Welcome to ThirdEye Labs, where we make the unseen seen. This is the Read Any ML paper, Part 3 Lab. We take the deepest symbols from a research paper, the Gaussian and the evidence lower bound, and build them ourselves in plain Python. Before we dive in, here is what you need. You should have seen parts 1 and 2 on notation, and you need a little NumPy. A first meeting with the Gaussian and KL divergence helps, but we build them from scratch here. Section 1. The plan. In the last video, we learned to read the deepest symbols, the Gaussian, variance, normalization, and the evidence lower bound that trains VAEs. Now we build each of those pieces by hand and assemble the loss on the real iris dataset. Section 2. The Gaussian. It is the bell curve of natural variation, like the spread of heights in a crowd. We write its density in one line, the exponential of -1/2 the squared distance from the mean, divided by the spread. Section 3. Log-likelihood. We take the log of that density. Working in log space turns a tiny product of probabilities into a stable sum. This is the reconstruction term, how well the model explains the data. Section 4. LayerNorm. This standardizes each row across its features. Subtract the mean, divide by the spread. Think of it as releveling the audio so every track sits at the same volume. The tiny epsilon in the denominator keeps a flat row from dividing by 0. Section 5. The KL term. It measures how far the encoder's Gaussian is from a standard normal prior. It is the extra surprise you pay for using the wrong map, and it is 0 only when the two already match. We use the closed form. Section 6. Put it all together, the evidence lower bound. We run one untrained pass on iris. A tiny encoder maps each flower to a latent Gaussian, and a tiny decoder reconstructs it. The bound is the reconstruction minus the KL. Because it is untrained, the number is low, exactly as expected. Section 7. Validate. We check every piece against the libraries. Our Gaussian matches SciPy, our LayerNorm matches PyTorch, and our KL matches PyTorch's own distributions. All three agree. Section 8. Break it on purpose. Feed LayerNorm a flat row where every feature is identical. The variance is 0, so without the epsilon we divide by 0 and get not a number. Add the tiny epsilon back and it is finite and safe. The scary symbols hid one simple guard. Section 9. Visualize. We plot the encoder's Gaussian against the standard normal prior. The KL term is the force that pulls the posterior toward the prior, keeping the latent space tidy. Section 10. A real-world use. The Gaussian log-likelihood we just built is a surprise score. We fit a Gaussian to the flowers, then score each one by how unlikely it is. We inject one clearly wrong measurement, and it lights up with the highest surprise, well past the threshold. This is exactly how the same machinery flags credit card fraud, factory defects, and abnormal medical scans. You model what normal looks like once, then ask of every new point, is this surprising? Let us recap what we did. We built the Gaussian density, its log likelihood, LayerNorm, and the KL term, all by hand. We assembled them into the evidence lower bound on real iris data and checked every piece against SciPy and PyTorch. The big lesson, even the loss that trains VAEs is just a handful of simple operations. That is it for this lab. Please like and subscribe ThirdEye Labs if you enjoyed it, and tell me which symbol you want decoded next. The full code is in the description.